Hello, everybody. Thank you for joining us today on Datadog On. My name is Brandon West, and I'm joined by a couple of our engineers here at Datadog. Brad Carter is a senior engineer, and Jason Thomas is a senior staff engineer. And we are going to be talking about WebRTC. The RTC stands for real-time communications, something that I didn't realize for a long time. But to start things off, Datadog On is a video series where we speak with the engineers that are building the features and operating the systems that power Datadog. So we have 45 minutes of content for you, talking about how we use WebRTC, what we build with it, how we build those features. And then we will have 15 minutes of Q&A for you at the end. So if you have any questions, make sure you hit that Q&A button and get those questions submitted. As I mentioned, my name is Brandon West. I'm a team lead on the developer advocacy side of things. I have a background as a web application developer, and I was part of the CoScreen team. CoScreen joined Datadog through an acquisition. We're going to tell you a little bit more about what CoScreen is, but it's one of our primary use cases for WebRTC here. Brad, why don't you go ahead and introduce yourself, please?
Yes, I am Brad. I've been working on desktop-y web applications for about 7 years. Joined CoScreen in October of 2020. Joined Datadog when we were acquired, and primarily been working on building like good user experiences and the a lot of the parts that you see for the CoScreen application.
Thank you. And Jason, you've been working with real-time streaming stuff and WebRTC since the very early days. So tell us a bit about yourself.
Hi, I'm Jason Thomas, the former CTO and co-founder of CoScreen. Currently, I hold the position of senior staff engineer at Datadog, where my primary responsibility revolves around infusing the platform with real-time communication capabilities. I have, as Brandon said, an extensive background in the streaming media space, which spans over a decade and a half. Before that, I was an embedded software engineer working on a particle physics experiment. I started working with standard broadcast media back during the transition to HD and ATSC. And then I moved to real-time video conferencing at a company called Source Communications, building video streaming pipelines from scratch with H323 SIP and H263. Here's where I developed one of the initial mobile sign language relay systems that brought a paradigm shift to communication for the deaf and hard of hearing community. Later, I founded CoScreen with my co-founders, Phil and Max, and about roughly 6 years ago. And as Brandon stated, we were recently acquired by Datadog. I'm excited to share my experiences with you today and delve into the fascinating world of WebRTC.
Awesome. Thank you, Jason. So a little bit more context before we jump in, just what is Datadog? Datadog is a monitoring and analytics platform that helps companies improve their observability and security postures for their infrastructure and their applications. Datadog operates at a pretty enormous scale with tens of thousands of customers operating millions of hosts that send tens of trillions of events every day. So the problems that our engineering and operations teams deal with are pretty massive at scale. CoScreen, I don't think is quite at this level yet, but hopefully it will be someday. So before we jump in, very briefly, let's talk about what is WebRTC. Brad, why don't you give us a quick overview here?
Yes, and then Jason, fill in whatever I get wrong. So the bulk of this is just it's all a bunch of protocols and APIs in order to make two computers talk to each other, which sounds easy, but it's not. There's firewalls, there's all kinds of hurdles you have to jump through. In addition to just sending data back and forth, it also gives us nice ways to manipulate media streams, so both audio and video. And it's up to the browser how they implement the standard, but most of them do a pretty good job. And then underneath this, it's powered, I think, by libWebRTC. Is that right?
But yeah, you're doing great, Brad.
Great. So yeah, I mean, it's basically, if you just want to take one thing from this, it is the parts that make communicating between two computers or more, yeah, simple.
Okay, so that's a quick introduction to WebRTC. So why do we use WebRTC at Datadog? Well, as I mentioned, the primary use case is enabling streaming data for CoScreen. So what the heck is CoScreen? Well, CoScreen is a next generation screen sharing and video chat application. The cool thing about it is it lets multiple users share multiple windows at the same time, and all of those shared windows are interactive and allow remote control. So it's got audio, video, it has captured window data being sent via WebRTC, and some other stuff in terms of metadata for remote input, and some other experimental features that we're going to tell you about a little bit later. So a little bit easier to show you what CoScreen is than to describe it. So we're going to hand things over to our founder, Till, who's going to walk you through a quick demo.
The brand new CoScreen V5 release. This is Till from the CoScreen team. Here the biggest changes that we've just shipped. So you can now toggle between the control mode and draw mode in CoScreen, so that you don't inadvertently interact with remote windows anymore. And you can deliberately choose how you want to click or draw into a window. And if you're not in any of these modes, you're not going to interfere with the window, unlike it was in the past. Many of you have told us about that. You can now move windows much more intuitively, as shown here. You can now bring windows to the foreground with just one click, so that they're not hidden anymore behind other windows. You can resize them smoothly, no matter if it's your own window or another user's window. You can bring the video chat UI to the top so that it doesn't get behind other windows. And most importantly, you can now share windows from multiple displays. See here, Max shares Terminal from his first display, shares Chrome from his second display, and both windows are visible on my display. And I might only have one of them. And even if you move them between displays, if Max would move them around, they wouldn't get unshared. So it's a much more frictionless experience in terms of screen sharing than what you've known from prior CoScreen versions or even other tools.
So there you go. That's announcing some of the features in the latest release, version 5, but hopefully it demonstrated what CoScreen is capable of. Sharing windows across multiple displays, multiple users, all interactive with video chat on top of it. Brad, Jason, anything I missed?
No, it's perfect. We can't beat Till.
That was a great demo. We should tell him he did a good job.
Yeah.
Till, you did a great job. Okay, so we mentioned some of this already in the context of that demo. So the things that were powered by WebRTC, the video chat, the audio chat, all of the contents of the streaming windows, which we're going to dig into a lot more, how that works. And then some other stuff that I talked about, cursor position, what clicks are being sent, keyboard input, all of that sort of fun stuff. So that's how we use WebRTC at Datadog. But why do we use WebRTC? Well, these are the 4 main reasons. AV is a really hard problem. WebRTC gives you good tools and a strong ecosystem. Most importantly, in my opinion, it lets the CoScreen team focus on what differentiates CoScreen as a product, which is the user experience and making screen sharing work in a way that it hasn't worked before. And then, of course, flexibility and portability. We'll talk a little bit about what that enables for the team in a moment as well. So, Jason, you have a ton of experience with AV, with streaming. It's a hard problem. Tell us a little bit about why it's a hard problem, what WebRTC helps us solve, and why we've built CoScreen on top of it.
So, I started in the broadcast media space, right? And in that area, that was already a hard problem because there's really difficult issues like AV sync's very hard because you think you have 2 separate sources of recording media. You have a hardware device, you have a camera, and you need to send them over a network through packet, put them into packets, send them all over the other network. They can get lost on that route. Pieces of them can be lost. They can be late. They can get deformed. They can get mutated in different ways. And then you have to recompose them on the other side and you have to sync them together. And just that problem alone is actually a very difficult problem to solve. And what you have in the network media space is you can buffer, right? So you'll notice with your YouTube videos, it sits there and just buffers 10 seconds of media. You have all of the audio and video packets together and it can sit there and it has all the time in the world to basically make sure that the audio playback and the video playback goes out together, right? If you're doing real-time communication, you have to be very, very aggressive at reducing the size of your buffer. And if you're doing something like what CoScreen's doing, where milliseconds count for interacting with a remote window, you have even less buffering, right? And so you have to use forward error correction. You have to use congestion control, and WebRTC right off the shelf provides all of these advanced mechanisms for delivering real-time communication that, things that I had to build in the past. We spent maybe 2-3 weeks building our forward error correction system for Sorensen. We had very little off the shelf, we're doing Reed-Solomon encoding, all this other stuff to try to figure out how to build this redundant packet redundancy system to improve our communication. And it's incredible how many videos you can support now, how much bandwidth there is now, and how much this technology with WebRTC has really improved the developer experience, and just given all of these tools off the shelf that are practicing sort of industry best standards in all of these different areas. So you don't have to focus so much on all these low level details. Knowing about them is very helpful, because when things go wrong, you can go in and debug them and figure out what's happening and stuff. There's plenty of that still happening, but you get this high quality, basically library right off the shelf that's in every browser, that you can even pull libWebRTC down and use it in an embedded fashion, and can get through firewalls, can get into the right networks, can do all of these things, even has observability. You can do Git statistics and stuff, and standard tools that are out there and standard protocols. It's a much different world than the one I started in terms of implementing real-time communication because of WebRTC.
So to summarize, WebRTC lets you move quicker and spend a lot less money because it brings all of the tools and well-known solutions together. Is that accurate?
Yeah, and also it makes an industry standard, so now other players in the industry can leverage the same tools that you're using to provide platforms and solutions in this same ecosystem that in the past you just have to build yourself.
Excellent. Brad, I think you can speak to the strong ecosystem and tools, because you came from the perspective of building user interfaces and desktop applications and that sort of thing without a deep understanding of the network traversal and packet optimization and session negotiation and all of that fun stuff.
Yeah, no, I didn't, and still don't know a ton of that stuff. I know a little bit, and I think it's important to know a little bit. But what WebRTC has gotten right is that the abstractions that it's laid out, they aren't perfect, but they are good enough that they allow other people to build chunks of functionality, so that I don't really need to really care about how the connection gets established. You need to know, you need to be able to make sure that you can debug it. But once it's there, then I can focus on, okay, now how do I make this look good? How do I make this feel good? What are the, we built CoScreen because we thought that traditional screen sharing was lacking. So how do now we can focus on that part of the experience, as opposed to, oh no, it failed to traverse that firewall and now the two people aren't connected. I'm not trying to minimize that problem, but WebRTC and then all the abstractions built on top of it allow us to focus on what is core to our value, which is just great.
Yeah, absolutely. And that brings us to the next hexagon there on the screen, which is it lets the team focus on screen sharing. Jason, you alluded to this a moment ago, where the thing that you're building is fundamentally different than just enabling chat via video. In video, you can have delays of maybe even seconds, and people won't necessarily experience that because it doesn't disrupt the flow of conversation or the type of interaction that person is trying to have. But when you're trying to click a button on someone's remote application and it takes a second for that click to go through, it's very jarring and it feels like an unnatural experience. So let's talk a little bit about that. How does WebRTC let us focus on just those experiences?
So originally the protocol actually didn't very much, but the other part of WebRTC that really helped us is it was open source, right? The implementation that Chrome provided in libWebRTC was completely open source. It was an open source version of actually Gibbs, right? And so you can go in there and it's just C++. And so we forked WebRTC, we went in and we changed the way that the buffering works and other things in order to get the latency that we want. And it turns out as we were developing that, people are probably familiar with other types of streaming solutions that are real time in the web now, because what's happened is WebRTC has added into the specification mechanisms for setting and adjusting buffering and doing things that allow very similar things to what we did when we forked WebRTC. But I think that's a big power that it has, in that there is this evolving specification, but because it's open source, you can get in at the guts of it and you can make it something custom and something even different from the overall standard. WebRTC as a infrastructure and all those other things, you don't have to give up the leverage of all of that system and the standards in order to, make the little tweaks that you want to make your value add product now. And so, there's a lot of people that are using it for just data channel, embedding it into their Node.js apps or their Rust apps or whatever, right? Because there are these open source implementations, you can easily kind of jury rig and paste into almost anything.
Excellent. And then I think another factor, I already mentioned this with the rise of web clients and that sort of thing, but portability is huge. We use WebRTC for CoScreen to enable clients on Mac and Windows, and the newly launched web client, which I think is huge. And we're going to talk about that again in a moment. But Jason, you just mentioned how people are now using WebRTC for things just like moving data around, partly because it solves the tricky problem of traversing these complicated network topologies. And we're not going to go too deep into all of this networking stuff, but for people who aren't familiar with how adding additional nodes to a network can increase the complexity, can you just briefly walk us through sort of this and how WebRTC helps address some of these problems?
So I think when WebRTC was first introduced, like the idea of pure connection was it was going to be this peer-to-peer sort of mesh network, which you can kind of see here, this four-way mesh network or something where you would basically have everyone connected to everyone else, right? And I think if you think about the problem, if I send a video to every single other person in this network, I have to transmit that video that many times to everyone else. There isn't a mechanism on the internet right now to achieve this type of broadcast. There's no multicast that is functional across networks that are local at this point. And so, you don't necessarily have the mechanism to send that data in. You have to send it independently, right? And so, you have basically the number of users times the bit rate of the media source that you're sending. And then the other problem is that these users may have differing network quality to you and to everyone else in the network. So now you're sending a video at a particular quality to everyone. And then, this guy in the red shirt has a worse quality network than everyone else. So you now have to reduce the quality of the video you're sending to the least performant peer in your network if you want them to be able to get that, right? Because you can sit there and adjust the bit rate of the video that you're sending and do other things to add extra forward error correction and stuff, where it would be better to send the high definition video. And so there's simulcast now, but now that increases the amount of bit rate that you're having to send, or you're having to not only encode like multiple versions of the video, there's SVC, but there's overhead for that. And now you're having to send it to all these different peers. And so what really the industry has ended up focusing on is SFUs, is having this kind of on the far end here on the right, having a distribution center, having a server that relays all of these connections, right? And so it kind of sucks because this peer-to-peer promise that WebRTC originally had is kind of, people still, you can make incredible peer-to-peer things. We use it for CoScreen for our remote control. We actually do a four-way mesh network if it's possible, but because that's going to be the least amount of latency you're going to get between each peer, but it doesn't actually for audio and video. It's much simpler to have this sort of infrastructure where you would have turn servers, you have sort of a centralized server, and it adds to your observability and a lot of other things. It makes things much less complex. And so, if you're starting out and you want to build any sort of multi-peer audio and video type WebRTC system, you really should from day one build around some kind of SFU or MCU or some kind of third-party service, because if you don't, going from the mesh-like network to that is actually very, very difficult. You'll paint yourself into a corner. And there's so many tools that these third-party providers have created around allowing you to kind of create the kind of experience that you want and observe it and observe what's happening with your clients, that it's just a much easier path. And so,
excellent. Yeah. So a few acronyms there, SFU and MCU. SFU, selective forwarding unit. Am I right?
Yes.
Close?
Yeah. So an MCU is like when back in the day when Cisco first came up with this idea of having this single server that's going to combine videos, the idea is you would have like a really fast piece of hardware. It would get all the videos and combine them all into like a single surface, and then it would rebroadcast that. And for mobile devices, that obviously is great because if you're on a 5G network, having 10 different connections that are all coming from a bunch of different videos, right? And different streams and stuff is a much more complicated. They're all going to get independently buffered. There's going to be all this other stuff that happens. Having a single video that comes down that's coming from one source is obviously better, right? But the problem is with cloud infrastructure, with hardware, MCUs are very expensive because they have to decode and re-encode all the videos. It has to do all this extra work. And so the WebRTC space has very much ended up focusing on SFUs, which is basically you send your videos to a bridge or to some kind of relay that then will send it to all the other users. It manages security, it'll set up end-to-end encryption. They have all sorts of things for observability, for looking at like, why did this stream go down? Or why is this user not getting audio and all these other things? It makes the problem of net firewall traversal easier because now you have this like independent mechanism. They can connect through port 443 with HTTPS, which is something that like most corporate networks only allow outgoing HTTPS on port 443 and stuff. So they've basically worked out all of these complex network solutions that if you're just using WebRTC out of the box, Peer Connection gives you a lot of tools, but you have to know how to use those tools in order to do the type of NAT firewall traversal and stuff that the protocol and the specification enables, and systems will do it for you. So
and just one other thing I want to quickly define is the NAT traversal. And the simplest way to say it is, if I have my own network and I've got an internal address for a machine, something on the internet needs to figure out how to get to it. There has to be a network address translation between that external address that my router or firewall is presenting to the world and that device internally. Okay, great. So some of that you just mentioned relates to what we're going to talk about next, which is how CoScreen deals with screen sharing. And this is something that's proprietary, that I think you actually have a patent for this algorithm, but you basically combine all of the different captured windows into one stream, do some of that SFU stuff you were talking about, and then allow clients to unpack it. Walk us through how that works a little bit.
So, in CoScreen, like we had this very difficult problem of like, how do we allow people to share however many windows they want, right? Because, if you're on Zoom right now, you share one window, it knows what the resolution is, it knows what the bit rate is. It's not changing, it's not moving around. And so, we capture all of our windows pre-compositing into the desktop. And so if you put your window off screen, if you put it anywhere, we're still capturing the content of that window. And then we're basically composing it onto this kind of virtual desktop. And what we do is we box pack all the windows, right? And so the windows that are the focus of the conference are going to be the big ones that are being streamed at full resolution inside of this kind of texture, which is a lot like if anyone's done game programming where you put textures into, you load all the textures as blocks into the GPU and they're all kind of gridded together, right? So we solve using a box packing algorithm how to pack all of these windows together, and then we scale them so that they all fit within a certain max resolution. And so here's kind of the algorithm actually from a wiki entry I made that's kind of explaining how this process works. But basically, yeah, you'll have these two desktops. So when D2 is like a vertical screen, D1's another screen. We take all these windows, and then you can see on the right, the box packing of those windows. It's figured out a solution, but it doesn't fit inside the max resolution, right? So now it's going to go and do another attempt where it reduces the scale of some of those windows, of the least prioritized windows, and then sees it if it fits, and then it does another attempt of scaling. So it'll keep scaling and reducing the size of the windows. So overall, the quality reduces over time. And this could be achieved through independent streaming of windows as well, but there's a lot of overhead, as we mentioned before, for renegotiation. You're adding additional connections, so there's more points of failure. There's a lot of benefits to packing all the windows in this particular system. And the other thing was our third-party SFU that we were using at the time didn't actually support multi-streaming. So something like Zoom kind of does a hybrid approach between combining videos like an MCU would and streaming independent streams. And at some point, maybe we'll move more in that sort of paradigm. But I think we're very proud of what we've achieved in terms of this. This is actually all a Rust-based library that's based on libskia that we've embedded into a library that has libWebRTC into it. So we kind of put these two things together to make sort of our proprietary streaming solution that enables us to do this thing that no other screen sharing application can do.
That's awesome. Very impressive stuff. Thanks for walking us through that algorithm. Next, something that this box packing enables is consuming those shared application windows in interesting ways. And one of the things that we've just announced that does that is the CoScreen web app. If you think about how things are done, how you would screen share, and how you would consume other people sharing applications from a browser, is fundamentally different. So here's a short video that kind of demonstrates how the web app works. And obviously you can't share because there's no window management in the browser that is analogous to what you get with an operating system. But here you can see those windows that had been composited and packed into that stream. You can choose which one you're viewing via the web app, and WebRTC enables all of the video and audio chat through the web app too. Brad, can you speak a little bit to how using WebRTC enabled the rapid development of the web client for CoScreen?
Yeah, so we use it's both a library and a service called Jitsi, and there are other ones. I think Jason mentioned Media Soup before. Effectively, it's a set of APIs that are built on top of WebRTC that allow us to build the experience that we are proud of. And what we ended up doing was, so much of the code that we use for the desktop application, because it's an Electron app running JavaScript, HTML on the desktop, we are able to take a lot of that code, run it in a browser, and then all of a sudden we're connecting from the browser into a desktop session. And in the initial prototype, it took about a week just to get that functioning where I could see myself. There was none of the window streaming stuff because that was a little more complicated, but seeing audio, video, and being able to see another person in the conference only took about a week. And without all the abstractions and the APIs that libjitsi Meet provides, it would have taken a lot longer.
Okay, cool. So we have a couple other features that Brad and Jason have been working on for a while that I think is super awesome. We have some cool announcements about this as well. But Jason, you've recently been working on real-time audio noise suppression. It's an often requested feature. People working from home want this so that when their dog's barking or someone's leaf blowing outside, it doesn't impact the quality of the meeting. It's kind of something that people expect. You implemented something that does this, and I think we can start by just sharing these samples so you can get an idea of what we're talking about. And then you can, I'd love to hear how you built this, how you made it small enough to be performant and fit in a browser and work real time. So here's original audio. This is Brad recording the source audio. He was outside at a meeting and there was someone mowing a lawn. So this is the lawnmower.
All right, so he's 15 feet from me, 20 feet away from me. And this is such a great real world test.
Okay, and then this is with the real-time noise suppression filter in place.
15 feet from me, 20 feet away from me. And this is such a great real world test.
So that's pretty impressive in my opinion. Obviously, it took a little bit of that low mid-range away from Brad's voice, but I can't hear the lawnmower at all. So, Jason, how did you build this awesome feature?
Okay, so I stood on the shoulders of giants, which is, there's basically the model that this is based on was trained and built for a Microsoft real-time noise reduction challenge. And it was built at a German university. And this was not the top performing model at that university, but the way that in that challenge, but the way that they built it was they tried to build it so it actually could be used in a real-time manner. But basically it came inside of a Python application as a TensorFlow model. And so the challenge for us was like, you look out in the world right now and everyone's using Zoom, everyone's using these experiences that are using, there's been this sort of revolution in AI-based noise reduction. As you can tell, it's incredible, like what it can do, right? And so it used to be in the past, people would hear pops and clicks and weird noises and stuff in audio conversations because what WebRTC provides out of the box is kind of last generation's noise reduction, last generation's echo cancellation, pre-AI and everything, right? And so, you go out and look in the world, and there's actually very few options out there in terms of any sort of solution that can provide this sort of next generation audio experience that customers expect. They expect to be able to filter out this kind of stuff and to have a high quality audio experience. And so, basically we found this project, and then, I spent a bunch of time, with certain tools. So the tools that kind of were the stars of the show were Rust and WebAssembly, right? So the idea was, how can we embed this in our desktop application in a way that will work on Windows, that'll work on our web application, and how can we shrink this model down and use it in a way that it would be performant enough that it's not going to be a huge CPU drain on our users. And so basically we get this model out, which is TensorFlow. And so first thing is convert that to a TF Lite model, which there's tools and everything out there to do that. We took that model, and then we, I used Rust to basically use the Mscripton backend, right? So there's two different WebAssembly backends. Mscripton kind of includes a host of POSIX-like tools that allow you to kind of write almost a program like you would write for a Linux system or something, right? And so we built, and then we had to process in the same way as the Python code, the audio samples, do a fast Fourier transform on them. And there were a couple of other things to get the audio samples into the right format and buffering. And there were a lot of missteps, a lot of things that actually went wrong, where it was too slow or would cause audio issues and stuff because the model was trained at a particular rate and a lot of other things. And so after a lot of time tailoring the solution, we were able to integrate it, and then it was too slow. And so then I had to go learn a lot about the fact that there's SIMD optimizations you can do in WebAssembly now. And actually on the M1, we were doing like multi-threaded performance. The M1 has like terrible performance for threading on for WebAssembly for some reason, something that hasn't been fixed for Chrome in a long time. But basically there was a lot of fine tuning and tailoring to kind of shrink this model down, make a Rust wrapper around it, build it in WebAssembly, and then get it to load into an audio worker, which is like audio worklets are these just, they have pretty much no environment. They had nothing for doing RAND and for doing like all these standard browser facilities that Mscripton reaches into. So we had to create a bunch of polyfills around that. But once we had all of that, we have this working solution that's actually integrated in CoScreen now. It's like we still have it as an experimental feature because we're kind of afraid of like this model can kind of do anything, but it's been being used for several months now by many people in our many of our customers and stuff. We've had very few complaints about it. It works really, really well. And we're thinking about packaging it up and open sourcing it, because I think it would be very good for the WebRTC community in general to have something that's kind of off the shelf that people could kind of add this level of sophistication in terms of noise reduction into their own platforms.
Yeah, that's an awesome story. I think I really appreciate how you took this published algorithm from some researchers at a university. Also very cool that they made it public. I think everyone else has kept theirs proprietary. So thank you for sharing. I think it's very cool that you're thinking about taking all of that work you did to make it performant and miniaturized and work in WebAssembly so it could be consumed by browsers and various clients, and sharing that back to the community. I think that's awesome. So everyone definitely stay tuned. I'm going to continue to poke Jason about that until he gets an engineering blog post written, and we can share that library broadly with everyone here. Very cool. Thank you for walking us through that. Brad, you worked on something, well, I want to say kind of similar, but different. Similar in that it uses machine learning stuff, and also that it's
AI.
Yeah,
we'll
exactly.
Get it into the transcript.
Yeah.
This is, I'm excited to talk about this. For context, when I joined, there was no video. It was just audio. So CoScreen did screen sharing, which was great. The quality was incredible. One of the reasons I took the job, Jason, I never told you this, but the screen, like being able to read the text was just so great. And then they had audio. And the way that we would see one another is we would open up Photo Booth and share the Photo Booth app on our Macs. And that's how we did video conferencing. So, shortly after I joined, maybe it was right as I was joining, they decided to add video in there. And ever since, people have been like, hey, we want to be able to blur our backgrounds. For me, my back here, you can't tell, it's a mess. trying to reduce the echo in this room, but I got this wonderful Zoom blur, sort of wonderful. And we wanted to build something like this, and it's not simple, and it's not off the shelf, which is just like kind of shocking given the ubiquity of the technology, and like the fact that, you know, you can find an open source model to put cat ears on my head, but like not blur my background. So what we did here was use a machine learning model from Google. They have a whole set of these. I don't know if they're branded or just packaged under MediaPipe. This one's called selfie segmentation. And what it does is it takes an input, so that's that far picture of me smiling on the left. And then it says, okay, where's person, where's background? And this calculation it's running WebAssembly. It takes like less than a third of a millisecond. So it's super, super quick. And then it passes you back two things. It passes you the source image, which is that image on the left, and then it passes you this mask, which the red part is me, the white part is the background. And from there, you know, I relied very heavily on this blog post that Slack wrote about how they built the background blur and virtual backgrounds for their application, because I thought that theirs was the best. It was better than Google Meet, better than Zoom. And so you take that image, that second one, and then what I did was invert it because it made it easier for me to think through the shaders. So a shader is a program that is going to basically run on every pixel in an image and do some kind of mathematical transformation. So what we're doing here is we inverted it. So now the background is red, the white part is me, and then the in between is the part where the model's like, we've blurred it a little bit to reduce some of the artifacts, but like you can effectively look at it as the confidence in the model. So like, how is that a hoodie or is that, you know, my earlobe? And at that point, that's where we're doing like something a little bit more sophisticated, but roughly you can think of the amount of blur reduces as the pixel becomes more transparent. So as you get closer to the white stuff in that third picture, the blur reduces. As you get closer to the red stuff, the blur increases. We're still working on how much is enough blur. Should it be less blur, more blur? Should there be blur options? And making sure that it's very performant. One of the fun things is was like improving the performance, and we got it down to Google Meet levels, partially by not segmenting every frame. So if I move my head pretty quick, you can see the lag on Zoom's background blur, and they're probably doing something very similar where, you know, your head doesn't move a lot in 16 milliseconds. So maybe we can skip, and every other frame we resegment, and we reuse the mask for a couple frames. And so we're able, by doing that, we can reduce the amount of GPU that we're using, which overall makes a better experience. It's a lot of fun. It should be off the shelf, and it was a really, really fun feature to build, because before this, I knew hardly anything. I knew nothing about image filtering or shaders or WebGL or anything like that. And now I know a little bit more than I did before, and we built something pretty cool. So this will be released in the future when it's good enough. I can't give you a date, but it'll be at least as good as the one I'm using now.
Very cool. I'm excited to see that option. I know lots of people have been asking for that as well. How about sharing this with the world? Is another thing that seems like should be available off the shelf. Maybe we can share that WebAssembly module as well, huh?
I think it'd be great.
Cool. Well, I'll be bugging you about that too, so we can share that with the world. I also appreciate that you leaned on Slack engineers and the work of others to build this. It's a common theme, especially around WebRTC, building on top of what the community has provided. And as you said, Jason, standing on the shoulders of giants. Big reason why CoScreen is built on top of WebRTC. So we are getting close to the end here, but there's one other thing we want to talk to you about when it comes to WebRTC and an experimental feature that the CoScreen team's been working on. So next, we want to talk a little bit about data channels. So Brad, can you give us kind of a brief overview of what data channels are? And then we'll talk a little bit about this fun experimental feature.
Yeah, I mean, back to the first question that you asked me about, like, what's WebRTC? Like, it's a way for two or more computers to talk to each other. The data is encrypted. You can send a message to either it's bidirectional. You get informed when new data is here. And for this, you know, we use it right now for communicating mouse positions and like when a user clicks, so that we can transfer that to the other computer. And with this feature that we're about to talk about called coterm, we're actually like transferring the output of a terminal or of a shell, the PTY data, and the sort of the diff that we should apply to the other terminal. It's more complicated than I'm making it, but basically we're transmitting terminal data back and forth instead of frames in an image. And we're using data channels to do it.
So let's take a look at this quick video. So what you see here is scrolling between a remote terminal and seeing the data. It's behaving like a normal terminal. And then here you can see this terminal on the right, the white background is a captured video stream of a window. So you see it's slightly blurry, and when Till runs this ping command, there's a touch of latency. This is the same thing via coterm with all of that data being transmitted directly. So it's a real terminal. There's no capturing involved. It's just piping the data directly. Jason, did I describe that accurately, more or less?
That is perfect. So essentially we have a PTY. Basically, we connect to a PTY, we create a virtual one, and we use the same technology that we use for everything else in CoScreen for remote control to stream it to everyone. And then we have our own in CoScreen client that renders it. And we will be also releasing a headless client, which can do it from your own terminal. So you can kind of bring your own terminal to CoScreen.
This is super exciting to me because it starts to show the other types of collaborative possibilities that can be enabled by something like CoScreen. Really, really cool. I know something you told me that you were working on. Can you talk about the entropy stuff, or is that? Yeah.
So I think we got approval to, we just can't show people how to use it yet, but we also are very aware of the fact that people are very sensitive about secrets sharing and stuff internal. So we've kind of developed a technology that real-time filters secrets out of the terminal. And we are using kind of a hybrid between a regex filter that can find and filter out secrets and a entropy-based secret filter. So like if you go and open up your ID RSA, with your private key in it, while you're in a coterm with someone else, it'll actually censor all of the secret data before it's even transmitted via the PTY to all the other users. So you'll see like a highlighted red background saying that, so something's been redacted, and everyone else will see stars with a highlighted background, so they know that they're seeing redacted data. But basically it allows people to use terminals to pair with each other, to teach each other about things, to maybe even connect into remote systems that in a secure manner that we're going to be integrating very tightly into Datadog itself.
Awesome. Yeah. That's very cool. I can't wait to play around with it. Any ideas when that might be releasing?
We have our OKRs this quarter. We're going to have basically the beta implementation finished. So I would say at the end of next quarter, we should have something for sure. So I'm not making any promises, it's still in active development, but we're eager to get it out and in people's hands.
Excellent. And I think both of you have mentioned that you think this data channels stuff is going to continue to be big, enable lots of real-time experiences in the browser, partly because it just can navigate those complex networks so well.
I think it's a key component to what we are wanting to do in Datadog, which is add real-time modality to Datadog. And so this is the technology of the web to do this sort of thing. And so I think we're leveraging all these tools we built to connect CoScreen deeply inside Datadog.
Excellent. Well, that brings us pretty much to the end of the prepared content. If you want to check out CoScreen, coscreen.co/download. You can also now try it out via web application. So you can do that as well. So now we have time for some Q&A, and I have a few questions here. To start off, and Brad, I think I'm going to point this one to you, since you're the most recent new person to use WebRTC. But if you were new to WebRTC, and when you were new to WebRTC, what were some resources or recommendations that you have for someone getting started?
Yeah, So there are lots of good resources. There's one called WebRTC for the curious, which is like a deep dive into how all of this stuff works, and you can read about all the acronyms that you want. But I think that it depends on kind of where you're at, what you're trying to do. If you are the founder of a company and you're trying to like, I've got a great idea for this revolutionary video conferencing technology, go read that thing first. If you're just wanting to play around and seeing like, well, how could I connect to browsers and stuff, like maybe you don't. Maybe you just find the API you need, you build that API, and you just roll with it. I think ultimately you have to go and build something so that you can figure out what you don't know. But it also depends on your temperament. I know some people like to read every piece of documentation before they write any code. That's not how I operate. The other thing I would really suggest is that you think about like, what is this going to be like? Because we were talking earlier that you can have the best, most beautiful architecture and system with the lowest latency. And if the UX, like if I have to share photo booth to get video chat going, like, people aren't going to use that. They want to be able to see my face. They want to see this mustache. They want to be able to interact with us. And that's and making sure that you do it in a thoughtful way that respects the table stakes of this game, right? So like good video, good audio, relatively low latency, stable connections. And then if you have to break those rules, break them, but like know what they are, and then make sure that you build something that is usable and worthwhile. And very vague advice, but that's what I would tell that person.
I think that's great advice for everyone, right? If you just want to learn, go build something. But if you're actually trying to build something people will use, then you have to stop and think about how you're going to present the cool thing you're building to them. Yeah, it's definitely great advice. Jason, do you have anything to add for someone new to the world of WebRTC?
Yeah, I mean, I totally agree with what Brad said. I don't know if I have a lot new to add to it. I'm like him. I like to go build things. And, like I definitely know when you build something and then it doesn't behave the way you expected and you're kind of falling off that cliff, then you go and read all the documentation, you master all those things. But like step one is to go in and try to make something. I think if you're going to understand any system, you have to start with having some hooks in it. So your brain is curious about learning those things. Because like Brad says, I don't think anyone likes to read RFCs. Nobody likes, maybe there are people, but like I like to read them because there's something exciting I'm trying to do. And I can't do it because something is breaking or something isn't working, or, I've tried a bunch of different things. And I think that once you do that, you'll start getting that kind of deep knowledge that you're looking for, because it's hard to build, even people are just purely academically interested in technology and just want to read all the documentation but haven't built anything. They're missing a big part of the picture, which is like, what are you even, why are you doing this? Why are you, and you can't actually understand the content as well as you want to unless you're making something. It's those failures, those mistakes, those gaps in your understanding, that those aha moments when you read something in the RFC that leads to learning, that leads to advancement in any skill set.
Absolutely. Awesome. Totally agree with that. And I think another way these days would just be to ask ChatGPT to generate you a video conferencing client, right? Using WebRTC. Boom, done.
Yeah.
Cool. Okay, Jason, this one's for you. We talked a lot about the benefits of using WebRTC, but it can't all be sunshine and roses. What's some stuff that WebRTC is not so great at?
Oh, so I think that, when I first entered the WebRTC space, there was like a holy war between different codecs, right? Like Microsoft wanted one thing and, Google wanted VP8 for everything. And so, and then there was a holy war over the protocol and design spec itself. People didn't want SDP, which is session description protocol, which is basically like how you communicate what features your client has to other clients so they know what kinds of videos they can send and stuff. As a protocol, WebRTC is pretty, I mean, I don't want to like disparage the work of the W3C, but it's insane. It's like pure connection. If you look at diagrams of like all the states it can be in and when it falls into different states and stuff. It's kind of mind-bogglingly complex. I know that there were other alternatives. They tried to do ORTC and other things to try to make stuff simpler. It's simple enough that like, you know, you can kind of put these pieces together and it's well understood enough. But when things go wrong, it's hard because it's definitely, you have to deep dive down into these low-level details very quickly if anything goes wrong. And it's not the most well-designed protocol I've ever seen. What's so great about it is it's like they took GIPs in libWebRTC, and Google provided a standard, some standard that where there was no standard before really. And they provided a standard implementation where you used to have to pay $100,000 to get it. But the protocol is very webby. It's taking something that's like low level and real time and trying to make a web API around it. And the web API that's around it has all these weird fields that some of them aren't used anymore. Things are deprecated. Things are, you know, so there's definitely some really nasty parts to WebRTC. It's confusing. It's a poorly designed overall protocol in my opinion, and you have a lot that you need to learn about it if you're going to get really deep into the details. But thankfully, there's really good wrappers that people have made. There's really lots of information that's out there. It's a standard. So, you know, Jitsy's built, Jitsi Meet, that's a great wrapper around it. Media Soup has lots and lots of examples out there. There's examples, and you're in good company to make use of it. But there's definitely lots of nasty areas in it that, you know, it's not all rainbows and green fields, you know. So that it's definitely a rough around the edges web API. So,
but despite all of that, still built a whole company on top of it and recommend it.
100% recommend it. You know, doing this from scratch would be impossible, and I know because I've done it from scratch in the past, you know, and it took a lot of time. And, you know, building something at the level of WebRTC and all of the, you know, device handling and control and the, you know, echo reduction and all of these systems, congestion control. It's no small undertaking for a startup, for any company. So.
Cool. I think one last question. How do you monitor WebRTC? How do you add some observability to what you built here?
So I can take that. So we're using call stats, which isn't great, right? And we also have our own custom admin portal backend, and we are, you know, we use Datadog, right? And we use something called Sentry as well. So we're using sort of a cobbling together of different pieces to kind of get, for one, traces when things go wrong, to get basically Peer Connection has a protocol or something called get stats, or an API to get statistics in a big JSON blob up. And then there's lots of third-party systems. There's something that's open source that's called RTC stats. There's if you're using OpenToke, if you're using AWS, there's lots of different ways to do it. The way that we do it is through what our platform provides, which is call stats, which recently got acquired by another company. And so we've actually built a lot of our own stuff kind of independently of that. And 8x8 JAS, they're replacing it with that open source RTC stats implementation that I told you about. But there's so many options out there, and, you know, honestly, a lot of them aren't great, but they're a lot better than flying blind. They're a lot better than having nothing. You know, if a client suddenly their audio stream isn't working, or if they don't get connected for some reason because there's some NAT firewall traversal issue, if you're doing peer-to-peer and you're not using some kind of stats collection system, you're just going to be flying blind. It's very, very important, if you're going to be building anything for production, to have some mechanism for collecting statistics. And there's lots of off-the-shelf solutions for that. I highly, highly recommend that you start with some sort of stats collection and client inspection system, so you know the state of what your clients are doing, because that's going to inform you and help you figure out and debug problems, because your customers will have problems. You will have videos freeze, you'll have audio drops, you'll have people who can't connect. That's just the world of the internet and real-time communication, you know, and it's you need the tools to deal with it if you're going to build a solution around it.
Wonderful. Well, I think that's the last question. Brad, Jason, thank you very much for your time today. I'd certainly learned a bunch. I hope the audience did too, and lots of exciting stuff to come. So thank you everyone for tuning in, and we'll see you again next time on Datadog On.